Imagine millions of people using electricity at the exact same time. Air conditioners running, factories operating, electric cars charging, hospitals working, and somewhere nearby, a massive AI data center suddenly demands hundreds of megawatts of electricity. The power grid has to respond immediately, because electricity isn't something the grid can simply store in unlimited quantities and use whenever it wants. Supply and demand have to remain balanced almost every second. And now, a new problem is appearing. Artificial intelligence is creating enormous new electricity demand at exactly the same time that many power grids are already agging. So how does the grid handle it? And what happens when demand becomes too much? Could the world's growing dependence on electricity actually push the power grid toward its limits? To understand the problem, we need to understand what a power grid really is. A power grid isn't one giant machine, it's a gigantic network. Power plants generate electricity, transformers increase or decrease voltage, transmission lines carry electricity across long distances, substations control and redirect the flow, distribution lines finally deliver electricity to homes, businesses, and factories, and all of these systems have to work together. Think of it like a massive highway system, except instead of cars, you're moving electrical energy, and unlike a normal highway, you can't simply allow traffic to build up indefinitely. The system has to remain balanced. If electricity demand suddenly rises, generators have to respond. If a major power plant suddenly disconnects, other generators and grid systems have to compensate. If a transmission line fails, electricity may be forced through other pathways, and if too many components become overloaded, the problem can spread. This is how a local problem can sometimes become a much larger outage. One failure can change the flow of electricity, that can overload another component, that component can disconnect, and the process can continue. Engineers call this kind of event a cascading failure, and preventing it is one of the biggest challenges in power engineering. Now add something new to the equation. Modern AI models require enormous computing power, and that computing power lives inside data centers. A modern data center can contain thousands of powerful processors. These processors consume electricity, and they also generate enormous amounts of heat. So the facility needs cooling systems, pumps, fans, power electronics, backup systems, transformers, switchgear, and a huge electrical connection to the grid. As AI systems become larger, the amount of electricity required by these facilities can become enormous. Recent research describes AI data centers as one of the fastest-growing categories of electricity demand and highlights the challenges they create for power systems. And this creates a strange engineering problem. The world wants more AI, but AI requires more electricity. More electricity requires more generation. More generation requires more transmission. And more transmission requires new infrastructure. The problem is, building infrastructure takes time. A power plant can take years. A major transmission project can take years. A new substation can take years. But a data center can be built and expanded much faster. In some regions, connecting a large new data center to the grid can take several years because transmission and interconnection infrastructure cannot be expanded quickly enough. So engineers are now looking for another solution. How can we make the existing grid smarter? One answer is advanced monitoring. Traditional power grids already use sensors, but modern systems can use enormous amounts of real-time information: voltage, current, frequency, temperature, power flow, equipment vibration, weather, and even the condition of individual components. All of this information can be analyzed continuously. This is where artificial intelligence itself can become part of the solution. AI can analyze patterns in grid behavior, predict demand, detect unusual conditions, and help operators identify problems before they become failures. Research published in 2026 is specifically examining how AI can improve grid planning, efficiency, and resilience, while also dealing with the challenges created by uncertain AI-driven electricity demand. Imagine a grid operator watching thousands of signals at the same time. Instead of waiting for a transformer to fail, a monitoring system could notice that its temperature and vibration patterns are changing, instead of waiting for electricity demand to spike. A forecasting system could predict the increase, and instead of reacting after something goes wrong, engineers can prepare before the problem happens. But prediction isn't enough. The physical infrastructure still has to handle the electricity, and one of the most important components is the transformer. A transformer can look simple from the outside, but inside, it's a carefully engineered electromagnetic machine. It can change voltage from one level to another. And high voltage is extremely important for long-distance transmission. Why? Because for the same amount of power, higher voltage means lower current. Lower current means less energy is lost as heat in transmission lines, so electricity can travel hundreds of kilometers more efficiently. But transformers have limits. They can overheat, their insulation can deteriorate, and extreme loading can reduce their lifespan. That's why grid engineers constantly monitor them. Another major challenge is the transmission network itself. Imagine a giant city suddenly needing much more electricity. The power has to travel through existing transmission lines, but those lines have limits. Too much current creates heating, and excessive heating can cause conductors to sag. That can create safety problems, so engineers have to decide. Should they build completely new transmission lines, upgrade existing conductors, build new substations, or use advanced control systems to get more capacity from infrastructure that already exists? Some grids are now exploring advanced conductors and dynamic monitoring systems to increase the amount of power existing infrastructure can safely carry. But electricity demand isn't the only thing changing. The sources of electricity are changing too. Solar power can produce enormous amounts of electricity during the day. Wind turbines can produce huge amounts when the wind is strong, but the grid doesn't control when the sun shines or when the wind blows. That creates another engineering challenge. Electricity demand may rise at exactly the wrong moment. For example, imagine a hot summer evening. Millions of air conditioners are running, but solar generation is falling because the sun is going down. The grid suddenly needs another source of electricity. This is where batteries become extremely important. Large battery energy storage systems can charge when electricity is available and discharge when the grid needs additional power. Instead of thinking of batteries as simply backup devices, engineers increasingly use them as flexible grid infrastructure. They can respond very quickly, they can help manage short-term demand spikes, and they can support renewable electricity. But batteries aren't the only solution. Some large facilities are beginning to develop their own power systems, instead of depending entirely on the public grid. A data center may combine grid electricity with on-site generation, batteries, or other energy systems. This creates what engineers sometimes call a power island. The idea is simple. If the grid connection is limited, generate some of the required power locally. This approach is becoming increasingly relevant as AI data centers demand more electricity and grid connections become harder to secure. But it introduces another challenge. If a huge facility suddenly changes its electricity demand, the local power system has to respond. And recent grid disturbances have shown why large data center loads need careful coordination. In one 2024 Northern Virginia event, a voltage fluctuation contributed to the simultaneous disconnection of dozens of data centers, creating a sudden power imbalance that required emergency grid adjustments. That doesn't mean AI data centers automatically cause blackouts. But it shows something important. Large new electricity loads behave differently from traditional demand, and engineers need to understand exactly how they interact with the grid. This is why the future power grid may become much more intelligent. Instead of electricity simply flowing from a power plant through transmission lines into homes and factories, the future could involve millions of sensors and automated systems constantly adjusting the network, solar panels, battery systems. Electric vehicles, factories, data centers, power plants, and transmission equipment could all become active participants in the grid. Electric vehicles could potentially charge when demand is low. Large batteries could discharge when demand rises. Data centers could adjust certain workloads. Power plants could respond automatically. And AI systems could coordinate everything. This is sometimes described as a smarter or more autonomous grid. But there's a problem. The more complicated the grid becomes, the more complicated its control systems become, and that creates cybersecurity risks. A modern power grid is not only a physical machine, it's also a giant digital network. Sensors communicate, control systems exchange information, operators rely on software, and automated systems make decisions. That means engineers have to protect the grid from cyber attacks as well as physical failures. A power grid of the future therefore needs to be both intelligent and extremely secure. And there's another challenge that people often forget. Extreme weather, heat waves can increase electricity demand because millions of air conditioners operate simultaneously. At the same time, extreme heat can reduce the efficiency of some power equipment and transmission infrastructure. Recent reporting has highlighted this combination as an increasing reliability challenge for electric grids. So the grid is being pushed from multiple directions. More electricity demand, more AI data centers, more renewable energy, more electrification, aging infrastructure, extreme weather, and growing cybersecurity requirements. This is not one engineering problem. It's several problems happening at the same time, and that's why simply building more power plants isn't enough. The grid itself has to evolve. Transmission networks need expansion, transformers need upgrading, substations need modernization, batteries need deployment, sensors need to become more advanced. Control systems need to become smarter, and engineers need better ways to predict what will happen before it happens. The goal isn't to create a grid that never experiences a failure. That's almost impossible. The goal is to create a grid that can contain failures, recover quickly, and prevent one small problem from becoming a massive outage. And this may become even more important as AI continues to expand, because the future isn't going to use less electricity. Electric vehicles will need it, factories will need it, data centers will need it, homes will need it, cooling systems will need it, and new technologies will create even more demand. The real engineering challenge is making sure the infrastructure underneath all of that technology can keep up. So the next time you turn on a light, charge your phone, start an air conditioner, or use an AI service, remember what is happening behind the scenes. Somewhere, generators are producing electricity. Transformers are changing voltage. Transmission lines are moving power. Substations are controlling the flow. Sensors are monitoring the system. And engineers are constantly balancing supply and demand. It all has to work together every second, because when it doesn't, the lights go out. But the future power grid is being designed to become faster, smarter, more flexible, and more resilient. And perhaps the most surprising part is this: the technology that is putting enormous pressure on the power grid. AI could also become one of the technologies helping engineers protect it. The next generation of electricity infrastructure won't simply be bigger, it will be smarter, and the race to build it has already begun. If you enjoyed this engineering documentary, subscribe for more stories about power systems, heavy engineering, energy technology, and the infrastructure behind the modern world. I'll see you in the next documentary.